key to the homework. I'd like to make sure I have all the homework before I return the homework. And he emails me, he's not going to be here today. So everybody still has to wait to
I
get their
know, we were
homework
getting
back.
onto him with stats. We're like, are you kidding me? He said, I haven't been home yet. I was like, go home.
Shouldn't have told him that. He should have come to class and then gone
Well,
home.
I didn't tell him that.
Oh, okay.
We were just like, go get it, but not like now.
Yeah, I didn't think he was going to go get it now.
Yeah.
Is that where he went? Was to go get that?
Well, I don't think he went just to go get it.
Oh, I was like, I get you.
All right.
Well, yeah, I'll hear that.
So we're going to move to chapter 4. And we're going to talk about continuous functions. What do you remember about continuous functions? Can you think of some functions that are and some functions that are not? Either in terms of, say, rules or the graph.
Piecewise would not be.
So piecewise would not be. So, or would likely not be, because we're on one piece for a while, and then we could be on some other piece for a while. And in terms of not, it's not continuous at one specific point. It actually is continuous everywhere else. But normally when we think kind of continuous, we're thinking continuous everywhere. But piecewise, where we change from one rule to another, likely is not continuous.
If there's a jump discontinuity or an asymptote.
So, an asymptote, so something like 1 over x, we're going along one way, and then all of a sudden we jump to something else. So we have one rule that defines it, and again, this one's not continuous at x equals 0. This is, I guess I didn't really say where this one is. At some value c, it's not continuous, but everywhere else it is. So in terms of continuous, there's kind of this idea that we can draw without any break. Or another idea, it's actually the one we're going to try to make more precise, is we actually arrive at where we're headed. So in terms of, say, this piecewise function, we're headed here, the inputs are headed to C, but the output isn't really what we expect it to be. Or on this one, the inputs are headed to 0. Are the outputs headed any place in particular? And at 0, do we actually get the output we expect? And on that one, the answer is no, because 1 over x isn't defined at 0. So there's that sense of we don't, in the discontinuous, we think we're headed one place, but that's not actually where we arrive. Well, in the language we've been talking about so far, a function is continuous at C if for each sequence x sub n, which is converging to C, then f of x sub n is converging to f of C. So we're looking at inputs that are getting closer and closer and closer to C, headed to C. Are the outputs really headed not just to some place in particular, but are they really headed to the value of the function there? And there's actually a little bit more to their definition that is included here so far. And so a function f, so we're talking about this function f being continuous at c, a function f defined on an interval c, or interval I containing C in its interior. And then also we need to add in each sequence x sub n in the interval I. We're not going to look at sequences that are outside the interval where the function's defined. So we can't talk about whether a function's continuous or not if it's just defined at one point, or even discrete points. We would not, in that case, even try to talk about whether it's continuous or not because it's not defined on an interval. We're also not going to talk about here what if C happens to be at one end or the other. So if we were looking, say, on the interval from A to C, and so even if, say, the function looks like this, we would not talk about continuity at either endpoint. Part of the idea of continuity is we have to be able to kind of look at the point on both sides. And the function still be defined on both sides of C. That we come back and we can modify that a little bit and talk about if we only come, say, from within the interval, do we actually arrive at where we are headed? But that's the idea of this definition. If we've got a sequence of inputs that are headed to C, can we predict where the outputs go? And not only can we predict where the outputs go, but are the outputs going precisely where f of, to the value that f of c is? So that would also take away an example we don't have over here in terms of not a function, say, that does this. This function would not be continuous at C as well. Because no matter what function of inputs we look at, the outputs are headed somewhere. It's just the value they're headed to doesn't happen to be the right value in this case. Now, this definition has, I guess, a little problem in terms of applying it. This if for each sequence, if we were going to do this for a particular function, and we will here in a little bit, we're going to have to think of how can I argue on every possible sequence that's converging to C. Because we can't just say, well, here's a sequence that converges to C and it works for that one sequence. That's not good enough. Fortunately, the flip is reversed. I mean, it is the case. If we find one sequence that goes to C and the outputs do not go to f of C, then the function's not continuous. So that one's easier to do, and that's has been our case all along in terms of disproving theorems. If we can find one example where the conclusion is satisfied and the hypothesis is satisfied and the conclusion is not, then the theorem's not true. So, this example, we wouldn't have to think of every possible sequence headed to C. If we could say, well, here's a sequence of inputs headed to C, the outputs are headed, say, to 2, but the actual value of the function is not 2, then the function's not continuous. And all we have to do is come up with one sequence. But we don't have to think of all the possible sequences. Because how many possible sequences are there that would converge to C? There are an infinite number of sequences, right? I mean, we looked at a few null sequences. So I mean, we could build a number of sequences that converge to C. So like, you know, C plus 1 over n, that would converge to C. C plus 1 over n squared, that would converge to C. C plus 1 over the square root of n. You know, there are all kinds of sequences that converge. There's really no, I mean, it is a challenge to come up with an argument built off every possible sequence converging to C. But there are a few times we're going to want to try to do that. So let's at least look at one example just to get a sense of what does this definition require us to do. So suppose we are asked, say, prove f of x equals about 3x minus 1 is continuous at x equals 2, using this definition. Now, this has been our challenge every time we saw this word prove, is to think, okay, what are the tools at my disposal? What do I actually have to do in this case? So if I'm going to prove this is continuous at 2 using this definition, what I'm going to have to prove is what I need to show is that for every sequence that converges to 2, that the sequence f of x sub n converges to f of 2, which in this case is, what was it, 5? Three times x minus 1. So this is what we're ultimately going to have to prove. That we've got this sequence of outputs that converges to a certain value, given we know something about a sequence of inputs. Now, since we're interested in needing to do this for every sequence x sub n, let's not try to pick one yet. See if we can just do this without knowing exactly what the sequence x sub n is, just knowing that it's headed to 2. I mean, if we had a specific one, that would make the problem easier, and I suppose if we wanted a sense of what this looked like, we could pick a specific sequence, but one sequence headed to 2 where it works isn't enough. We've got to build an argument with every sequence that's headed to 2, we know something about the outputs. So this is the statement we're going to have to prove. And so the proof of this is, given an epsilon greater than 0, let x be something, such that when n is greater than x, we get down to f of x sub n minus f of c is less than epsilon. I mean, that's how we prove a sequence converges. So happened a couple times on the homework set. We need to prove a sequence converges, so given epsilon, let's pick a capital X and show that when we're past that capital X, we really have our sequence close enough to the limit. Now, we do here at least have a specific function. You know, we don't have the sequence, but we do have a specific function. And so our challenge is to begin to think, okay, how am I going to do that? And so, how do we often start convergence problems? That's what our proof ultimately looks like, but how do we try to figure out what capital X was? Yeah, we would do what I was calling a preliminary analysis. That says, let's start with f of x sub n minus f of 2 less than epsilon, and hope that leads me to some estimate on, well, how big does n have to be? So let's see if that happens, what that does here. So here, what's f of x sub n? F of x sub n, we have the function f, 3 times the input minus 1. Okay, what can I do with that?
Would be easy just to simplify first.
Okay, so we start simplifying. What do we have here? I mean, minus 1 minus a minus 1. So this is what? 3x sub n minus 6. Okay. So that's a little bit simplified.
Factor out 3.
Okay, let's factor out a 3. And we get to this divide both sides by 3, and now we may think, yeah, I was hoping for an idea of how far do I need to go out in the sequence. And it looks like here, it's not working out like we've seen other ones. Because we don't know what the sequence x sub n is. You know, it might be 2 plus or minus some formula in n, and maybe we could figure out how big n has to be. But as we think about this, is there any way we might possibly know that x sub n minus 2 could be made less than epsilon over 3? Notice we did have this hypothesis. For every x sub n that converges to 2. So we don't know what the formula for x sub n is, but we do know it's headed to 2. What does that tell us?
2 minus 2 is 0.
Yeah, eventually x sub n minus 2 is as small as we need it to be. do we now have a sense of how small we need it to be? Well, if we can get it less than epsilon over 3, that should make the rest of this work out right. Since x sub n converges to 2, there is a capital X such that n greater than capital X gives us the absolute value of x sub n minus 2 less than epsilon over 3. I was looking for an x here, that when n was greater than x, something happened. So I now have an expression for x. It's not at all like we've seen before. It's much more abstract. But we have this sequence that is converging to 2. So once I tie down how close I need x sub n to 2, since it does converge to 2, there is a point past which I know something about that sequence. And in this case, the something I want to know is, oh, well, it's less than epsilon over 3. All right, so how do we kind of take what we've got here in the preliminary analysis and put it in our actual proof? So I think we have to say a little bit more. We can't just say, well, pick x to be this. But given epsilon greater than 0, by the convergence of x sub n to 2, there is a capital X such that n greater than capital X implies x sub n minus 2 is less than epsilon over 3. And as we've encountered before with problems like this, without the preliminary analysis, we're kind of left with this statement, well, how did I know I was supposed to get that less than epsilon over 3? And how did I know that was kind of where I needed to start the problem? Well, in our preliminary analysis, that's where we kind of got to and realized, oh, wait a minute, x sub n is going to 2, I can make it as small as I need to. And now I know how small I need to make it. So since x sub n converges to 2, once I decide how small I need to make x sub n minus 2, I am guaranteed there's a place past which I know what always happens. So, yes?
So is your capital X the same X as an X sub n, or is it a different one?
I mean, this capital X is the one that goes along with the x sub n sequence. So I'm using convergence of x sub n to 2, and notice this also then kind of frees me. I don't have to know what sequence x sub n I'm working with. Someone has given me some weird sequence, but since it converges to 2, for that weird sequence there is an x past which x sub n minus 2 is however small I need it to be. And I've decided here how small I need it to be is epsilon over 3. So we don't have a formula for capital X, but we do have kind of a recipe for how do we figure out what capital X is. We work with this sequence. We get to within epsilon over 3. We know we can always do that. Since x sub n is converging to 2, player B in the epsilon x game always has a winning strategy. We play an epsilon, a closeness. Player B always has an x they can pick. And past that x, this is always true. And now, just as before with the preliminary analysis, we work our way back up. So for this same x, well, again, I'm not even sure I need to say that. So continuing with this, 3 times the absolute value of x sub n minus 2 is less than epsilon. Multiply 3 to both sides. When n is greater than this capital X. We can put in the absolute value. 3 and the absolute value of 3 are the same. Product of two absolute values is the absolute value of the product. This is 3x sub n minus 1, then minus 5. Kind of looking here how I needed to split it up. And that is f of x sub n minus f of 2 in this case. Is less than epsilon, and we've accomplished what we set out to do. For an epsilon, we produced an x, different than we probably were expecting, but we produced an x. Past that x, we could reason that yes, f of x sub n minus f of x, or f of x sub n minus f of c, really is less than epsilon. Now, where we're going to be headed with the idea of continuity is really more of what does being a function being continuous mean for us? What kind of conclusions can we make about continuous functions that we can't make about just any old function? So, if we know a function is continuous and maybe some other things, what kind of conclusions? That's what we'll get to the next time. We will not do a lot of working through to actually prove functions are continuous from the definition. And in fact, we'll also develop another definition of continuity, because in calculus, our definition of continuity was definitely not based off the limit of a sequence. It was based off the idea of the limit of a function. The limit as x approaches c of f of x. Not just a sequence, but just the limit. And we haven't talked about that concept yet. We've only done limits of sequences. So we've definitely approached, sequences we didn't get to in calculus till the end of Calc 2. But we talked about continuity pretty much in chapter 1, I think, of calculus. So it came pretty early, the idea of continuity, the idea of a limit. So we've definitely flipped things here. We're doing limit of sequences first. But a function's continuity can be defined in terms of limits of sequences as well. Sequence of inputs headed to C. Can we know for sure that the outputs have to be headed to f of c? And for this particular function, the answer was yes. Yes, we could. The inputs headed to 2. We can make them small enough so that the sequence of outputs really is headed to f of 2. Is always small enough. Now, the idea of continuity we've looked at so far has been continuous at one specific point. In this example, we looked at 2. In a very real sense, this argument could be modified to work for any other point. It wouldn't be that hard to modify this to work at any c we wanted to. It's a little harder to follow that, but not a lot harder. Just change the 2 to some c's all the way through. we could do this so it works really for any C. But at least as we start, the idea of continuity is a local feature, right at a point. But if f of x is continuous at each point C in an interval, we say f is continuous on that interval. Or it could be any other set. Fortunately for us, most of the functions we're used to dealing with are continuous. X to a power, positive power, that's continuous. Some constant times x to a positive power. The sum of two continuous functions. The product of two continuous functions. Stays continuous. The composition is usually continuous. We'll have to talk a little bit, because there could be some domain issues there. Trig functions are continuous, or I guess sine and cosine are continuous. The exponential is continuous, absolute value is continuous. The things that we have to watch out for, the division of functions where the denominator is 0. I mean, fortunately, even divide two continuous functions, it's still continuous, except possibly where the denominator was 0. Piecewise defined functions are not continuous, or potentially not continuous. A function we use fairly often, let me see if I can get a graph of this. is what's known as the greatest integer function, or also sometimes called the floor function. Different books will give a different notation. I think this book uses sort of double bracket notation. The greatest integer less than or equal to x. So if we just think about the graph, what if x is, say, a half? What's the greatest integer less than or equal to a half? 0. What about a third? What about 9/10? What about 0? Yeah, 0 is still 0. So from 0 all the way up to 1, the greatest integer gives us 0. What happens when I plug in 1? We're to 1. 1.1? 1.7? 1.999937? So we jump up to 1 and we stay at 1 for a while till just before, well, everything but 2. At 2, we jump up to 2. What about negative a half? Negative 0.5. So is negative 0.5? I mean, from our graph here, what would you think? Negative 1. I mean, we kind of think a little bit. So, I mean, in a sense, the reason it's called the floor function. So, say you're at some decimal level, so you're half a floor behind, below ground level, and you fall. You're going to fall to the first floor below ground level. You're going to fall to -1. You're not going to be in the middle of the area there. When you fall to the floor you're going to hit is at a level of -1. So we are not just chopping off the integer part, or chopping off the decimal part. For positives, you can think of that's what we're doing, but for negatives, we're not. We're working our way back. What's the first integer as we move left? So let's see if I can get this to graph here. So do I have just a regular grapher? I can put that in here. I should. Yes, I do. Here it is. I guess it's the floor function here. So the floor of x, I graph this. It doesn't specifically indicate kind of where it starts and where it stops. From here it is hard to tell what exactly is the floor at 1. Between 0 and 1 it's pretty clear. Between 1 and 2 it's pretty clear. Not quite so clear right at, say, at 1 or at 2. Now, the reason I wanted to graph this, if we do this with a graphing calculator, I think I can do this with a graphing calculator. And one thing we've got to watch with the graphing calculator, if we ask the graphing calculator to graph y equals, and here I think it may be the integer. So the integer of x notice we still kind of get the stair step looking, but even if we do the zoom, decimal on this. So we're evaluating it only at nice points. When we trace this, we're at 0, 0, 0, 0, 0, 0, 0, and then it jumps to 1. The graphing calculator, in its default mode, it connects the dots. It draws a continuous function, even if the function's not supposed to be continuous. It draws continuous, because it's just connecting the dots. And if there's a big jump from one dot to the next, it can connect them. In this case, it should not, but it can connect them. If we were to graph this instead with the dot mode, we get a graph that looks much more like what we have here in GeoGebra. Now, as we think of compositions, I wanted to look at this because let's do some composing of things that are not continuous, or at least one thing that's not continuous, and we can get some other, I think, unusual things. So suppose we take, say, this one. Instead of the floor of x, let's do the floor of 1 over x. Anybody have a guess what they think the floor of 1 over x is going to look like? Well, let's see if we can make sense once we've got it. So we've got this particular function. Notice from 1 on, that is 0. If we think about that, when x is bigger than 1, 1 over x is less than 1, the floor of something between 0 and 1 is 0. Between 1/2 and 1, 1 over that is between 1 and 2, the floor is 1. And we get this, and this, and this, and this. So here's a case between 0 and 1, we've got an infinite number of discontinuities, but there's still intervals on which this function's continuous. I mean, between 1/2 and 1, this function's continuous. It's the same value. Between a third and a half. I guess between a fourth and a third. A fifth and a fourth. A sixth and a fifth. A seventh and a sixth. There are some where it's continuous. I don't know at what point. Let's see if I... I can still kind of see it there. If I spread this out some, yeah, we still kind of see. So there are some intervals where we do have continuity, but those intervals get shorter and shorter and shorter. And eventually, if I bring this close enough, it actually also begins to connect the dots, even though it shouldn't. I think if I spread them apart, it realizes, oh, those aren't really supposed to be connected. I'm not going to connect them. But it is better at just not, oh, let's connect all these dots. But here, there does come a point at which, it's connecting the dots as well. So we get lots and lots of discontinuities. They really kind of pile up at 0. But there are still intervals on which we have continuity. Suppose, we change this just a little bit, what if I take that minus 1 over x? Try to blow this back up a little bit. The floor of 1 over x minus 1 over x isn't heading off to infinity. In fact, it's staying, it goes between -1 and 0, but we still have a small interval where it's continuous, oh, then there's a jump, continuous, then there's a jump, continuous. So an infinite number of discontinuities between 0 and 1, but still lots of places where it's continuous as well. So we definitely have to watch with composition of some things. We can get some rather bizarre functions. Let's see, if I did another of my notes here. suppose we had, let's see if I can do this. So the sine of pi over 4 times the floor of x. Actually, I want the floor of x in the numerator. And notice, its use of the floor is just one bracket with a little line at the bottom, sort of falling down to the floor. There's also a ceiling function which goes the other way. You let a balloon go and it rises to the ceiling, whatever ceiling, the first floor, second floor, wherever you happen to be with that. But let's see what this graph looks like. So we get a kind of interesting looking graph here. It's either, well, it's 0 for a while, then it jumps up to probably root 2 over 2, and then 1, and then root 2 over 2, 0, minus with that. If I took this, then minus, let's see, sine of pi over 4 times x. Get another kind of weird looking function. So definitely some jumps, some skips, but there are intervals on which it's continuous. Over most intervals we want to consider it is not a continuous function, but there are some small, short intervals where it's continuous. In fact, it's continuous between every pair of integers. Between 6 and 7 this is continuous, 7 and 8 is continuous, 8 and 9 is continuous, 9 and 10, 10 and 11, just not from 8 to 10. Because there's a discontinuity between 8 and 10. So in 4.1, let's see, in the section, you can look at 1b, 5, and 8, and at the end of the chapter, 2 and 8. Just working a little bit with the idea of continuity. Next time we'll come back and think, okay, suppose we have a function that is continuous and maybe something else. What kind of conclusions can we make about it? So we're really going to be looking more at things that follow continuity, but we need to get a better understanding of how are we going to treat continuity, for now at least, in advanced calculus. So I will see you Friday. And yes, Friday, we're going to have class Friday. Sorry.
I may or may not. I'll let you.
You may or may not, huh?
Might have to get a food shop on Fridays.
Where's the football game this weekend?
We'll have one.
Oh, that's right. I guess I did see that. So.